So earlier I introduced the symmetric model, the time fixed effects. Now we are considering S, which is specific to a certain year, but same for all states, same across the states. So for a while, let's only consider the time fixed effects. There is no state fixed effect now, just for simplicity of the presentation. And then how can we estimate this? Idea is exactly the same. You you just need to think about how to cancel this guy. So earlier, like so when you had state fixed effects, we considered two different years, say 1982, 1988, and if you take their difference, the state fixed effects are cancelled out because it does not change over time. However, the state fixed effects could be understood as different intercepts across different states. But now, exactly the same. The role of state is replaced by the time. So now the intercepts are different from time to time, from year to year. So this year the fatality is higher for all states, but in another year fatality rates are lower for all states. So the starting points are different across time, not across states. Then you may think about uh, year specific intercept lambda 1982. This is year specific intercept. And for 83, there is another intercept. Beta does not change. Beta 1, the effect of beer tax does not change, but the intercept changes. Like if you think about 1984, there is another intercept. And so there are 7 years in our data. So there are 7 different intercepts for each year. Then how can we cancel that out? There are, as before, there are two different ways. First, you may write the regression equation as this. You may include year-specific dummies. Define year dummy variables for 7 different years, but you have to drop one of them. So in the end, you are going to include the dummy variable for the second year and up to the last year. So t minus 1 dummy variables can be included. They capture the yearly differences. Alternatively, you may just write it this way. Of course, this is much simpler to write. So other than the slope, your intercept changes over time. Lambda t. Lambda is the intercept, which depends only on time. So this is called time effects equation, time effects model. Then how can we estimate? You may include t minus 1 dummy variables. This is not bad, not as bad as before, because usually the number of time periods is usually smaller than the number of entities, number of individuals or states. Also true in our model. The number of states is 48, but number of years is only 7. So it's much easier to handle these dummy variables. By the way, as I said, we are dropping the first year because if you include all dummy variables, they will cause the perfect multicollinearity problem. So you have to drop one of them. Usually the first one or the last one is dropped. But if the number of years is larger than like ours, like if it's too large, then it is not easy to include all the dummy variables like this. In that case, as before, we need to cancel out the time effects. The time fixed effects need be cancelled. So previously we considered entity demeaned method. Entity demeaned is considering, so like you subtract the average over time within an entity. So within a state, you observe 7 observations in one state. So take the average of 7 observations over time, over 7 years. But now we are going to year demean. You subtract the average over 50, like 48 states over the states at a specific year. Say in 1982, you have 48 observations from the states. Then you can calculate the average of 48. That is the average of 1982. You are subtracting this 1982 average in 1982, and do the same for 1983, 4, 5, 6, 7. So like that, you are subtracting the average, but you have to think about this. The average is calculated over states because remember the purpose of doing this is because we would like to remove the fixed effects. But the fixed effects change over time. In this example, now in this slide, the fixed effects change over time, but same across states. So when you take the average, you have to take the average across the states, right? Previously, in our state fixed effects case, we took average over time because the fixed effects need be cancelled, but it varies across states, but constant over time. So we take average over time. So you have to take average over the dimension for the dimension that has no variation. So it's same. So taking average does not change the part. So in the end, it can be cancelled out by taking the difference. So that's the intuition. And the same intuition holds in the same way. The problem is when you have both. This is, in practice, this is the standard model. When you have a panel data, maybe the most reasonable, maybe the first model you can think about in your dissertation or in your like research, whatever, like term paper later or in your report later, I would recommend you to consider both because that's natural. It's like both effects exist in most cases. And then, how can we handle that? It is not as simple as before. We would like so the idea is simple. The intercept changes across states at the same time across time, but they have a certain rule, like the intercepts are added, and then now you have to think about this. There are two different ways to implement that. First one is including the dummy variables. That was one possible way, and the other was demeaning, taking the subtracting the mean, subtracting the average. So, and we used two methods, and previously I emphasized the demeaning method because it is more convenient. However, when you have two fixed effects, it's not easy. You cannot cancel out them at the same time. So then our approach is we use dummy variables for one dimension and use demeaning for the other dimension. So like think about this. You may demean the entity dimension and include t-1 time indicators. So use dummy variables for the time dimension and demean and cancel out entity dimension. Or vice versa, you may cancel out time dimension but include dummy variables for the entity. Or you may include both dummy variables, or you may, if possible, you may cancel out both dimensions. I think it's not possible, not simple. So it is, I think, mathematically not easy. So the choices are the first three options. And of course, the problem, remember the main problem was a large number of dummy variables. and usually the large number happens with n. If t is greater than n, then of course you have to use this method. So canceling out t is more efficient than canceling out n if t is larger than n. So you have to cancel out as much as possible. So either this or this, but usually the first one is our choice. Especially in our case, by demeaning, we are canceling out 48 parameters and then instead including 6 dummy variables. 6 is not bad. 6 is totally fine. So we choose to include 6 parameters. This is that. You need to generate the dummy variables. So generate, gen is short for generate, and define a new random variable y83, which is defined as on logic. This is a logic. So year equals, so this is conditional equality. So this one equality was definition, and two equalities show whether they are same or not. So if they are same, it takes 1, otherwise 0. In the parentheses, it's a logical operator, logical indicator. If the parenthesis is true, then it is 1, otherwise 0. So two equalities is a conditional logical operator. So whether the data considers whether they are right or not. And you need to do that for 6 different years: 83, 84, 85, 86, 87, 88. And here it shows an interesting command. Global year dummy is defined as quotation marks 83 through 88. So I will show you this later, but it means that you abbreviate the line, the phrase in the quotation marks as this year dumb. Global is like you are going to use this abbreviation all the way till the end of this code. So it's global definition. Globally, you are going to use this definition. And then as you can see, later when you need to use these 6 variables at the same time, instead of writing this long sentence, you may simply write $yeardumb abbreviation. So then this is replaced by this in the line in the quotation marks. So, but in this case, you don't need to do this because you are using this only once. But if there are variables that is repeatedly used, then you may simplify the set of the list of variables like this. It's just a useful tip. So later in demonstration, I will show you how to do this. Anyhow, again, you set the panel data structure earlier and then use xt regression and fatality rate, beer text, and year dummy variables. Because we observe 7 years, we include 6 dummy variables. And dropping the first one, we observe from 82, but 82 is dropped, and comma fixed effects. Fixed effects, this option handles the state-specific fixed effects. So usually fixed effects handle only the state-specific effect. Year-specific effects have to be handled by yourself, like this, including dummy variables. And data only considers the statewide, like the entity dimensional fixed effects. And then the results is given this way. So all these six parameters are estimated, but it's okay because we canceled out 48 parameters. So it's much easier to read what's going on. And what's interesting here is there is a huge drop in 85. I don't know what happened. So there is a huge drop in 83. It has a large t-stat, and also a huge drop in 85. The other guys among these 6 dummy variables, the others are not significant, but there are only 2 years which have significant impact. I don't know what happened. For some reason, in 83, the fatality rate dropped in all states by this much. Also in 85, fatality rate dropped in all states by this much. Don't know why. And beer tax effect, the effect of beer tax is still negative. However, the p-value is now 8%, which is greater than our significance level 5%. So unfortunately, it's not significant. It's not significant. So that's what we see here. And you can test joint testing like this. Test and we use the abbreviation again, ear dummy, and then automatically it will calculate whether all the ear dummies are jointly 0 or not. The answer is p-value is only 0.18%, which is smaller than even smaller than 1%. So it's very statistically significant. So the ear dummies are doing something. They are useful in the model. Okay, so I'm in the next slide. I will consider the required assumptions, what we need to think about before applying this model. So, and of course, we are going to do stata. I will do the stata again at the end of this slides with homework. So don't worry too much about not following the stata. It's more efficient to use stata instead of slides to show the commands. Okay, see you in the next video. Bye.